So let's talk about oxyacids. This would be the last group of acids that we're going to talk about in this chapter. So what are oxyacids? Well, these are acids that contain hydrogen, oxygen, and one other element. Now, in naming these compounds, we do not express the existence of hydrogen in the acid name, and that's because the word acid at the end of the name will indicate the presence of hydrogen. So that's one big difference between naming oxyacids and binary acids. If you remember, all the binary acids that we talked about, their names start with hydro. So you have hydrochloric, hydroiodic, hydrobromic, hydroselenic, and so on. In the case of oxyacids, we do not start off with hydro anything because in the case of binary acids or in the case of polyatomic oxyacids, what you'll find is that the acid name indicates the presence of the hydrogen. So an example would be sulfuric acid, H2SO4. It's not hydrosulfuric acid, that is something different. It is simply sulfuric acid because it contains hydrogen and it contains sulfur and of course contains oxygen, which makes this deoxyacid. And the acid part of the name indicates the presence of the hydrogen. So that's basically the convention that is adopted by IUPAC. Now, the name of the acid is pretty much based on the name of the corresponding polyatomic ion. So if the name of the polyatomic ions end with ITE, then the ending of the acid name would be OUS followed by acid. If the name of the corresponding polyatomic ion ends with ATE, then the name of the acid ends with ic acid. All right, so that's how we can derive the name of the acid based on the names of the polyatomic ions. And of course, you'll have access to the names of the polyatomic ions because you'll be provided that list of that packet, which contains a list of common ions, which include polyatomic ions. One thing I want to point out here, and I think I discussed this earlier, but just in case I haven't, the ite and ate ending of the polyatomic ion does not indicate the actual number of oxygen atoms present. However, if you have an ion ending with ITE and you see a corresponding ion end with ATE, everything else being the same in the name, then you know that the ATE ending indicates one more oxygen compared to the ITE ending. All right? And we're going to see some examples right now. So, the sulfide ion, if you look it up, you'll see that it is SO2 minus, SO3 2 minus, I'm sorry. The corresponding acid will be sulfurous acid, right? So you see the ITE ending is replaced with OUS, all right? And the formula for the corresponding acid is H2SO3. And you'll notice here that for every negative charge that is present, 2 hydrogen ions are added. So therefore, the final formula for the corresponding acid will be H2SO3, all right? Here's another example. Now, this is a sulfate ion, which has one more oxygen compared to the sulfide ion. So that means that the corresponding name of the acid, the corresponding acid, is sulfuric acid, and the formula will be H2SO4. Again, 2 hydrogens are added for every 2 negative charge that is present. In the case of the nitrite ion, which ends with ITE, the corresponding name of the acid is nitrous acid, so the ITE ending is replaced with OUS. And in this case, we would just add 1 hydrogen ion to the nitrite and the formula becomes HNO2, all right? In the case of the nitrate ion, for which the formula is NO3 minus, the name of the corresponding acid would be nitric. So here we replace the ATE ending with ic acid, and the name, or I should say the formula for the corresponding anion will be one where hydrogen is added, or the hydrogen ion is added to the nitrate formula NO3 minus, and the formula now becomes HNO3. All right. So this is another list of different anions and their corresponding acids, and the same rule applies. All right. And these specifically are the oxyanions and oxyacids of chlorine, and they're similar relationships when it comes to other halogens, bromine, iodine, not fluorine, because fluorine do not have any, there are no compounds or anions that are oxyfluoride ions. So the same rules apply as I said before. Now, there's some variation here because, for example, in the case of the hypochlorite, We have hypo, and then we have chlorite. The name of the corresponding acid is hypochlorous acid. In the case of the chlorite, the name of the corresponding acid is chlorous acid, and so on and so forth. So pretty much the same rules apply, with some variation because we have hypo and per in the case of these two here. All right. Now we see that when it comes to the oxyanions of halogens, bromine, iodine, and chlorine. And these are some other examples that some of which we have met before, like the sulfuric from the sulfate, the sulfurous from the sulfite. There are others which follow basically the same rules, like bromic acid formed from bromate ion, oxalic acid formed from the oxalate ion, phosphoric acid formed from the phosphate ion, and so on. Okay, so this is just a summary of the rules of naming compounds. Just to briefly go through this flowchart here, polyatomic compounds, if you have one category over here, acid, which begins with hydrogen. If you have an anion contained oxygen, then we check the ending of the anion name. If it's end with ITE, then the name changes to OUS acid. If it ends with ATE, the name changes to ic acid. For other polyatomic ions, basically we give the name of the cation and the name of the anions. And we talked about the rules about the names of the cations when it comes to the stock system and so on. Okay, so that is basically the end of this chapter. So we're going to move on to chapter 6 in the next video. All right, until next time.